describe to you some work we've been doing in recent years to try to think about how to incorporate some of the information we're getting from high-resolution observations of galaxies, to try to do something about how we model star formation in cosmological galaxy formation simulations. So here, to start with, I'll show you a picture of the dark matter simulations. So for the past 2 decades, simulations of collisionless dark matter have played a key role in establishing the concordance cosmology, and they've completely transformed our perception of the universe. So it seems that the universe is dominated by dark energy, and that galaxies owe their existence to particles that we have yet to detect. Right? So we don't know what they are, but we're very good at simulating them. And why do we believe that this dark matter is there? Well, we believe that the dark matter dominates the gravitational field, and the gas follows this dark matter cosmic web. We believe that the gas collects in dark matter halos, and if we do the simple exercise of associating a galaxy with all the massive dark matter halos that we see in the dark matter only simulations, we very nicely recover the statistical properties of the distribution of galaxies in the sky. And so here we see a famous plot of Volker's, where in blue you see the observations, in red the simulations, when you just play the simple exercise of associating galaxies to the dark matter halos. So you recover the size of the structures, the size of the voids very nicely. But when you then ask yourself the question, how many stars form in these different dark matter halos, and at what rate, you find very quickly that going by what happens to the dark matter doesn't quite give you the answer. So here you have a picture of the mass function, so the number of objects of a given mass, and the prediction from the dark matter simulations. If you draw the mass function that you get and scale it by the baryonic mass fraction, you get this line here. But when you measure the mass function of galaxies, what you find is that what you would predict from the pure dark matter simulation over-predicts the number of galaxies you get, both at the low mass scale and at the high mass scale. So not easy to figure out how much, if you make a simple assumption that the most massive dark matter halos form the most stars, right? That's the simplest thing you can imagine, you will not match what the observations are telling you. So there is this simple relationship in the meantime that is uncovered by people who look at the star formation rate. So here's a plot, a very famous plot of the surface density of the star formation rate versus the surface density of the gas mass. And what you find is that it obeys a very simple power law relationship over many orders of magnitude, which spans galaxies from starburst to the centers of normal disks, suggesting that the star formation rate scales as the gas density to some power, which happens to be 1.4, which looks like, perhaps, it's an indication that the star formation rate proceeds on a dynamical timescale, on a free-fall timescale. So we know the free-fall timescale goes like the density to the 1/2 power. And so when we plug that relationship in for this free-fall time, we nicely recover a very similar exponent to what you see in the observations. So the thing is, of course, is that this is a plot here, this sigma gas here, includes atomic and molecular gas. In the meantime, since that kind of measurement has been made, there's been an explosion of multi-wavelength observations. And so here I'm showing you just one example of a particular galaxy seeing at different wavelengths. So here we have a plot of what this galaxy looks like in the dust emission. Here we have what it looks like in the H-alpha emission. Here's the atomic component, the molecular component. And what's most striking about this, what you see right away, is that the tracers of recent star formation, so whether it be the dust that's heated by the newly born stars, or the H-alpha emission, those tracers are most closely followed by the molecular gas map. So without doing any quantitative measurements, just by looking at this, you get a sense that what's associated to the star formation rate is this molecular gas, rather than all of it, the atomic gas. Now what do we know about this molecular gas? So we can think about what kind of lifetimes the structures containing molecular gas have. So here's an example of M51, so a massive spiral galaxy, grand design spiral. And here you see the different points tell you correspond to the masses of the different structures, the different molecular associations or complexes in this galaxy. So you see that the most massive ones very nicely line the spiral arms, and you have these much smaller ones in the interarm regions. And if you believe that the molecular associations assemble these spiral arms as the galactic potential rotates, and then as the potential rotates, these complexes are shredded and end up in the interarm regions, you can estimate a lifetime for these associations to be about 100 megayears. But if you look at much smaller molecular clouds, such as some local ones, so here's an example of the Taurus-Eureka complex, and try to estimate the ages of those 10 to the 4 solar mass molecular clouds, and you come up, you find that you don't find any stars much older than about a few megayears associated to the molecular gas, which points to a much younger age for these molecular clouds, which perhaps can be explained by thinking about them forming in some kind of collider flows. Right? So you can imagine streams of atomic gas, to use an example of such a situation that Fabian Height used to be used, we did years ago. So we looked at streams of atomic gas and at their interface when they collide, the compression. The gas compresses, cools, fragments, and forms some dense structures which perhaps one could associate with the early sites of star formation. So if we go back now to this plot, I showed you that there was a tight correlation between the star formation rate, surface density, and the gas density. If we instead scale this gas density by free-fall time, you find a very tight correlation between this. Right? And here, we're not just plotting averages, we're not just plotting these quantities over entire galaxies in the local universe, so that's what we would get here in the shaded region. We're looking at individual molecular clouds are being plotted here, as well as clouds or galaxies at different redshifts, so both high redshift, local redshifts. And they all obey this very nice relationship. And so from this plot, right, if star formation is indeed happening on a free-fall time, you would expect the slope of this line to be unity. But what you find instead, that the slope of this line is only about 0.01. So what it tells you is that the molecular gas is forming stars on a time scale much, much longer than the free-fall time. So if you have this molecular gas and you wanted it all to turn into a galaxy, all of it to turn into stars, you'd have to wait about 100 free-fall times, right, for that gas to all turn into stars. But in fact, when you look at the free-fall time, which is about a few million years, those molecular complexes we saw, they don't live that long, right? They don't live long enough to turn them. So what this points to is a very dynamic lifetime for these molecular structures where we believe that the stars are forming. So somehow, the belief is that the molecular clouds somehow form or assemble and form stars, so a small fraction into stars, and then disperse by some dynamical process before the entire initial molecular content can turn into stars. So here's another, so let me convince you more that the molecular gas has a very dynamic character. So here's a picture of the torus cloud color-coded by velocities. So I think it's the blue is the slowest, and the red I think goes up to about 12 kilometers a second. And so here, you really see that in this structure. So this is a local molecular cloud, very dynamic character. And you can quantify that by looking at this other very famous plot. So here you have the Larson relation, so which is a measurement of the velocity dispersion on a certain length scale. And what is found is that it obeys a very tight relationship, and the slope that you get out is an indication that it's compressible turbulence. But it's not only compressible turbulence, because when you look at this, we know that molecular clouds are nearly isothermal, so very cold, approximately 10 Kelvin, which corresponds to a sound speed of about 0.2 kilometers a second. And so what you see is that the gas, not only is it compressible because of the slope, right? You also see that it's supersonic, right? Because most of it lies above the sound speed that you associate to its temperature. When you then look at where the stars form, so we know more and more of these beautiful images, maps of molecular clouds. So here you have a picture of the Perseus molecular cloud from the core to disk legacy survey. So in the gray you have the extinction map, which gives an indication of the surface density of the gas. And then the points here are protostars, or the first stars that are forming before they even have a chance to migrate from where they form. And what you see what's very obvious, of course, is that the stars don't form uniformly through this structure. They really form in these high density regions. And when you go back to your Larson scaling relation, you see that you can associate the place where the turbulence transitions from supersonic to subsonic to a length scale of about a tenth of a parsec, which we call the sonic scale. And what's really remarkable is that there are now observations which claim to detect this transition from the supersonic to the subsonic. So here is an image, and let's just focus on the left side of this picture of the gas map of Perseus cloud, mapped to the ammonia molecule. And so what you see is where the protostar forms, you are in this very calm region where the turbulent velocity dispersions are subsonic, and when you walk away from that region, the velocity dispersions increase. So this has been described very poetically by Mr. Goodman and Paolo Caselli. These are the islands of calm in the turbulent sea where the stars are actually forming. And this indeed, this picture here is the postage stamp of the model that we're trying to implement in our simulations. The idea that perhaps the protostars, the stars are forming in the places where the turbulence dies down. Now, of course, Ralph can tell you, he's done these experiments many times. We know that the simulations tell us that isothermal, supersonic, compressible turbulence decays very quickly. At a free fall time, it decays. So one thinks about how do you sustain it, how do you drive it. And what we come up with many mechanisms, many internal processes, jets, supernova explosions, something that will keep the gas stirred, keep the velocity dispersions high. But yet, in the interstellar medium, you also find turbulence, so indications of turbulence, such as this, so this kind of filamentary structure, in places where it's hard to come up with a driver for the turbulence, right? So even in non-star-forming molecular clouds, where we cannot invoke things like protostellar jets, we will have indications of gas turbulence. Now, of course, we need to look at a little further, so not just focus on the one molecular cloud, because as you saw in 51, these molecular clouds live in galaxies, right? And so there are other processes, so other than internal ones, that can be driving the turbulence. So here, for example, is a simulation of a self-gravitating, differentially rotating galactic disk, right? And so here, they zoom in on a particular region and find that the structures, the clouds inside, when you look deep inside at higher rise, you start to see the fragmentation of the structures. And so perhaps what we're seeing here is the energy of the differential rotation in the gravitational potential on large scales cascading down into these small structures and driving turbulence interior to them. So also what you see very nicely in this kind of simulation is that these larger structures, right, they interact with each other, right? So pulling material, so there are torques, right? So it's another source of energy for driving turbulence inside the structures. So if we go back to this canopy plot, this very, very famous plot, right, that suggests that the star formation rate scales with the gas density, right? So there you have, so it's a one parameter relationship, right? And we said that maybe this is just telling us that the star formation rate increases like low to the 1.5 hours. We can use that, and indeed this is the common thing that people use, to model how we form stars in the cosmological simulations. So in its simplest form, the model says that if the density in your gas cells is greater than some threshold density, so if you're in a high density region, let's form stars on a free fall time so that we recover this 3.5 power here. But then we have to think about what this efficiency is. And we saw, right, the observations tell us that efficiency has to be very, very small, so about 1%. Now, when you look at this, what you see is that you have a parameter here, right? What do you take with this threshold density, right? Is it going to be resolution dependent, as it generally is in a simulation? So the better the resolution of the simulation, the higher you take that threshold. But of course, we know that as a simulation, cosmological simulation proceeds, right? Perhaps the density in the galaxies is higher at higher redshift than the average density of the galaxies, higher redshift than at lower redshift. So do you just take this one threshold, or do you have to have a varying threshold? So here we have a resolution-dependent parameter. And of course, this efficiency here, if you take it to be fixed, right, it's not a prediction of the simulation. It's a parameter, right, taken from these observations. So what we've been doing is trying to think about what the observations of supersonic turbulence has been telling us. So here's a picture, again, of a molecular cloud. So this part, the quiet one. So even in the quiet ones, what you recover when you measure a histogram of how much gas you have at different densities, so that's what this plot here is a very nice distribution called the log normal distribution. Right? So very simple distribution, which in fact has been a well-known thing that the isothermal supersonic compressible turbulence give you. Right? If you run one of those simulations and make this kind of histogram of the gas density, you get this distribution, this logarithmic probability distribution function. So it has two parameters. It has the average density, rho naught, and there's a width to this distribution. Now the width of the distribution depends on the Mach number of the gas. Right? So this, of course, is sensible, right? It makes sense because the Mach number gives you an idea of the degree of compression in the fluid, right? So the width of your distribution, of your probability distribution function, tells you the range of densities that the gas achieves. And so you can imagine that if you have higher Mach numbers, you can reach both much higher densities, but also much lower densities, right? So it makes sense that the width of this distribution function can depend on the Mach number. But in recent years, Christoph Federer and Ralph have made a nice point that the width of the distribution also depends on how the turbulence is driven. Right? So here is an example of two simulations. So they're pure ground box isothermal simulations. The same initial kinetic energy, but the way the forcing is done in the two simulations is different. So in one case, the forcing is solenoidal, in the other case, the forcing is compressive. And so what do we mean by solenoidal? So some kind of stirring motion, very simplistically. So this is the kind of forcing that you can imagine would be relevant when you're considering forcing by differential rotation in a disk. The compressive forcing, much easier to come up with many mechanisms, right? So supernova explosions, expanding H2 regions, jets, many things that can cause the gas. And again, without me doing anything quantitative, you see by eye that the range of densities you achieve in the simulation with a pure compressive forcing is much greater than the range of densities you achieve in solenoidal forcing. And indeed, when you go through the exercise of plotting the histograms for the distribution of mass, for how much gas you have at a given mass, you find that the solenoidal forcing simulation has a much narrower width. So indeed, in the log normal distribution, there's not only the Mach number, but also the time of forcing that goes into it. So, how can we use this to try to build a model for how to do star formation? So the answer is, if we believe that gas, star-forming gas, has this kind of generic log-normal PDF, and if we can come up with a way to figure out above what threshold density the gas will collapse to form stars, we can simply integrate above that density, right, to come up with a star formation efficiency for freefall time. So in general, so there are different ideas for what to take for this critical density. And so the one that we use is we look at the density above which the Jeans length becomes smaller in the sonic scale. And so it turns out it can be given by this kind of formula which introduces another parameter, which is a measure of how much kinetic energy you have, how much gravitational energy. So with this kind of thinking, you find that now, instead of your efficiency being one number, so being 1%, what you find is that it depends on the local dynamical properties of the gas. So in this case, the Mach number, the forcing, so whether the ratio of solenoid to compressible forcing, and this variable parameter, which tells you how much kinetic energy to gravitational energy you have. So, of course, this integral here only tells you, it gives you an estimate of how much gas is likely to collapse, to become gravitationally unstable. But it doesn't tell you how much of that gas actually becomes a star, right? So now it turns out, of course, that the dense, so it gives you an idea, if you like, of the dense core mass function, but not the stellar initial mass function. But because their shape is so similar, the claim is that you can scale, once you know what this is, you put a little coefficient here, which tells you, okay, about half of that gas becomes stars. Half of the gas goes right to Schumann's and becomes stars. But to convince you that star formation efficiency is no longer constant. Here's a nice plot. So for a fixed ratio of the solar element to compressible noise, so you can look at how the star formation efficiency per free photon varies with the variable parameter and the Mach number. So you see it's not a constant anymore. And you can take different values depending on these liquid dynamical properties that are sensible, right? So if your cloud, if your gas is dominated by kinetic energy or the gravitational energy, so you expect that the star formation efficiency should decline. Similar, right? If the Mach number is increasing, so there's compression, you might expect that your kinetic energy increases. So there's an analytic theory to this, to computing the star formation efficiency, but it's been tested on numerical simulations. So meaning there have been numerical simulations, so isothermal with sync particles for the stars that measure this efficiency, and you can figure out how they match them with the theory and how it's very close. So back to finally telling you how we've changed the star formation recipe. So instead of choosing the sites of star formation by looking at a density threshold, we instead look to see where the gas, where the gravity overcomes velocity support. And in the velocity support, you have not only the non-thermal motions, but also the thermal motions. Okay? So this goes back to that picture of that the mapping of the protostar, the islands of common turbulent sea, right? So we look for the islands of common turbulent sea to identify where we're going to find the stars. And then we still make them on a Schmidt. We still do it with a Schmidt law. And now our efficiency, instead of being one parameter, it depends on the local dynamics of the gas. Now, in reality, we don't measure the forcing. This is something we have to measure on the fly. But the Mach number and the variable parameter is something that we measure on the fly on a cell-by-cell basis. So the simulations that we're going to now take you very quickly through the results. So what happens when you change the star formation recipe? So you saw, if you want to start thinking in terms of this kind of model, you have to start getting to decent resolutions, right? So kiloparsec scale resolutions in your simulation will not work with this kind of star formation recipe. So here, I'm going to show you results from a series of AMR, so adaptive measure random simulations, which we call them not. And so these are simulations where a galaxy, where 5 times 10 to the 11 solar mass galaxy comes up to 0. And the resolution in the finest level is 10 parsec visible. And what else should I tell you? So we run the same simulation over and over again, and we just change the physics so that we can have a nice comparison. So you should appreciate, right, that the galaxies, when they form in these mathematical simulations, so all the results I'm going to show you is for a galaxy that sits here. So this is just a piece of the volume. And this picture here is color-coded. So green is gas density, red is temperature, and blue is metals, right? So the supernova explode and couldn't medium. So you see that the galaxy here is forming at the intersection of a complicated web of filaments, right? With some satellites coming along, so they do not sit. There is definitely environment playing a role. They don't have a simple life, these galaxies, as they form. I'm going to show you results from 6 simulations. Okay, there's going to be one set which uses the traditional density threshold star formation recipe with a fixed efficiency. And there's going to be another 3 simulations that are using this, what I will call the dynamic star formation recipe. So there will be the 2 simulations with no supernova feedback. Then there will be 2 simulations which have what I'll call the energy preserving supernova feedback, where the energy is put in instead of bubble. And then there will be a 3rd set of simulations where where we recognize that sometimes you don't have the resolution to resolve the energy conserving phase, which tells you that the momentum should go with the square root of mass. And so we end up, so when we dump the energy just in this energy form, it gets radiated before the momentum has increased to the value we expect it to have at the end of the energy conserving phase. So you can see here, these are rough numbers here, but you can see that if you don't resolve the energy conserving phase, you could underestimate how much momentum you have by a factor of 10. And so the third implementation tries to check. So it's an algorithm that checks whether the resolution is there to capture the energy conserving phase. And if it's not there, then the energy is injected in the form of momentum. So here we go. So here are pictures. These are projections of the gas density within about a tenth of the Barrier radius at redshift 3. So on the left are the results for the traditional star formation recipe. And on the right are the results for the dynamic star formation recipe. So again, the top row, no supernova feedback, and the middle row, energy feedback, bottom row, momentum feedback. So that's the density plots. Here's the temperature plot. So, okay, since I flipped it, I'll go back to it in a second. So top row, the traditional star formation density threshold feedback, and the bottom row, the new implementation of star formation feedback. Okay, so right away, then, just looking at the pictures, so there are a few things that I hope come across. So one is the thickening of the disk. So there's changes not only in the disk, what's happening in the disk, but there are also changes in what one might call the circumgalactic medium. So the effect of changing this recipe is changing both, I believe. So I'm going to quickly go back to my earlier pictures. So here's the temperature. So we have a comparison of the two simulations. And so you see, with the inefficient feedback, which is probably not capturing all the energy that you would expect to be available from supernova, the outflows are confined in both simulations very much near the disk. And it's only with the more efficient feedback, and for really in the extreme case, really boosting the IMF to Chablis from south here, so to try to get the maximum effect. Right? You see that now you can heat the gas much further out. And with the new recipe, it's striking that you get much higher outer region. And again, in the temperature plots, you see very clearly that the structure that you see in this outer region here is less pronounced from the structure that you see in these regions here. And again, you have a sense very clearly of the size of the thickness of the disks. So you see it in the pictures.
Excuse me.
Yes?
I have difficulty to understand the long gas temperature between minus.
This is a mistake. I'm sorry. You should be nice. Sorry. Thank you. I'm sorry. So Mark made these movies just a few days ago. He had to change it. But, right. So this is gas density plots. And so rotating. And so I didn't say this. The way they are oriented, all of these galaxies are oriented in a way that, so what Mark did was he found the angular momentum of the galaxies determined by the stars. And so these are rotations around the angular momentum axis. Okay. So let me try to show you a little more quantitatively the different effects of these recipes. So one of the things you could ask is how do the different recipes change the shapes of the galaxies that you get out? So what we did was we fit ellipsoids to these different gas distributions. And here the measurements are done just on the cold gas, okay, but it doesn't seem to change all of the mass. And so top row, again, is with the density thresholds of the traditional star formation recipe, and the bottom row is with the new star formation recipe. And so you should see three lines with the two dashed ones, and then when they're right away, you can read off. You saw visually that we have disks. So the lowest, the bottom ones are of course telling you the thickness of the disk, so measuring the minor axis and the ellipsoid. And the top two curves are giving you an indication of how spherical the disk is in the other two directions. So if you have a perfect circle for your disk, right, the two axis lengths should line this 1 to 1. So the other line, which will be drawn in all of my plots, are these vertical dotted lines, which are, so these are our guesses, if you want to define where the disk radius ends. The way we define it is we look again at the angular momentum vector, and we dot product that with the spin, with the minor axis that we know is an ellipsoidal fit. And where the spin of the gas and the stars match, up until that radius, we say it's a disk. Okay, so this line tells you up until which radius the spins of the star and the gas match. Okay? So you see in this picture, what I want you to get out of this picture, is that what you hopefully saw that I was showing in the movie, is that the thickness of the disk in general is greater with the new star formation recipe. So you see here, let's just for simplicity, even without any feedback to possibly thicken the disks, you will get a thicker disk. So here, to guide your eye, these horizontal lines, one at 10 parsec, which is at a resolution unit, and one at 100 parsec. And so here, as a function of radius. So what you see is that without feedback, most of the gas in the traditional recipe collapses into a very thin disk, which is not the case with the new recipe. Now, why do we think that that may be? So here are similar kind of plots of top of density threshold star formation, bottom one is the new one, the dynamic star formation. And here I'm showing you density profiles. So in green are the stars, in pink is the dark matter, and in black is the gas. And again, I just drew these horizontal lines to guide your eye. And these arrows are those disk radius that I mentioned a minute ago. And so what you see is that in the traditional star formation recipe, we form more stars in the center than in the new recipe, right? And we have more gas in the, which by default means we have less gas in the center than in the other recipe. So the other striking thing, of course, is that even the order of the density profiles, right? Here you have stars, dark matter, gas. Here you have stars, gas, dark matter. Right? Even the order has changed of what's dominating in the center. And this, I think, is one of the keys to one of the kind of things that plagues galaxy formation simulations, is that with this density threshold star formation recipe, there's a tendency to form stars preferentially in the center of the galaxies. And indeed, so that's what's coming up in these plots. The other thing, so only, I should say, it's only with the feedback, with the Chagrin on that, with this momentum feedback, that you find a way to suppress the peak in the gas density in the center. So the other thing that I commented on when I showed you the movie was that there was also an effect on how much gas you have outside the disk when you change the recipe. And so this, I think, is comes across clearly in these plots. So again, here's the top row is the density threshold star formation, the bottom row is this dynamic star formation recipe. And so even without feedback, you can see that in the new recipe. You have more, so blue is cold gas, red is hot gas. You have more, and you populate this region here, which is not, it's not cold. And so what we think is happening here is that, it's a complex thing that we're still trying to get our head around. But we think that by changing the distribution of the different components, the density profiles, right, it changes even the behavior of the material that's coming in. Right? So they're experiencing different potential as they come in. And so first of all, they're going through a disk that is more gas-rich, right? So as they go through, you can imagine that perhaps they carry out more stuff that they put back into the CGM. So there's that issue. So the other thing I meant to say, is that the thickening of the disk, we think, also is related to the fact that we have more gas in the disk. So a gas-rich disk is more unstable. Stars stable as the disks. So by having this gas-rich disk, your chance of the gravitational fragment driving some of this turbulence that I was mentioning when I showed the high-res simulation, simulation, and perhaps thickening the disks as well. And finally, so the effect on the rotation curves. So this, I think, was the thing that was most dramatic. So the top row again, density threshold star formation, is the dynamic star formation. And so let's just focus on the gas. So the dashed lines are the circular velocities. So when you figure out what the circular velocity should be for all components of dark matter, stars, and gas. And so if the disk is in rotation, if the gas is rotating, you expect its velocity to trace the circular velocity. And so in general, that's when you define the disk. And so, of course, the striking thing is that just by changing the star formation recipe, so even without feedback, you have a way to suppress the peak in the rotation curve at the center. Right? So here you see it's going up to 500 degrees, up to 300. So this galaxy at this redshift, this is all redshift 3, is only, it's about 10 to the 11 solar masses. Okay? So you expect the rotational velocity to be something like 100-ish kilometers a second to be flat. And so here, the normalization is still wrong. It's not what we expect for a dark matter halo or a galaxy that size. And so it's not, we're not saying that we don't need the feedback. The feedback, we find, brings down that normalization. Okay? But the point is that, that the traditional star formation recipe, even with the feedback, the normalization is too high. We form too many stars. So this is a problem that we believe cannot be solved just by increasing the resolution of the simulations. Right? We've done this exact simulation by cranking up the resolution to half the parsec instead of 10. In fact, the peak in the center of the rotation curve just shoots up even higher. Right? Because again, if your recipe for star formation depends on the density threshold, you will preferentially form the stars in the center. And once the stars are there, you can't get rid of them. Once they're in the center, right, you're stuck with this huge amount of gas. So it's not that, in the no feedback case, it's not that the simulation, the two different star formation recipes, produce a different amount of stars. The star formation rates in the no feedback case are similar. And in fact, at redshift 3, we have similar amount of stars in the galaxies. So it's not the rate of star formation that's the key thing. It's probably where they are forming. Now, as soon as you put in the feedback, then of course there's a coupling between the star formation and the feedback. And then it does matter. If the stars are forming with this recipe where we're looking for the gravitational unstable places, those places tend to be clustered in such a way that when the supernovae do go off, they affect the total stellar mass much more. So indeed, what we're seeing here is this sequence of plots where we change the star formation, the feedback recipe, so no feedback and the progressively stronger feedback. And what we find is that with the most extreme feedback, we've brought down the stellar mass by about a factor of 10 if we get the no feedback, whereas with the traditional star formation recipe, it only goes down by about a factor of 2. And finally, you might want, I started off by showing you these plots of the Kennedy-Schmidt relation. So here's a plot of the star formation rate versus the gas density divided by the technological time, with in blue observations from Emmanuel Daly. And again, in red, the traditional recipe, and in black, the dynamic star formation. And so you find that even though we are not using this 0.1 efficiency, even though that's not a parameter of our model, so we have an efficiency that's very low over the place. We still get our points to within reasonable closeness to what the observations tell us. So I will end here, and I'll say that I talked to many of you today. I see many of you are running these high-res and high-res simulations, and I think that we're at this point where when we run these high-res simulations, we have to rethink like a subgrid how we model physics. And so even the simplest things can't be taken for granted, so how we form the stars. And so I hope I've convinced you that, whether I'm not saying that this is the solution, I'm saying that if we try to inform our models by the observations that people in high-res simulations are doing, it seems to have potentially very trivial consequences